just put you on mute, everyone. So remember to hit the space bar when you want to answer. This is just the last question, just to get you into the doing it by hand method. So in this question here, they had 100 people, and it was, I think, a blood pressure question. So the mean of this 100 people, their blood pressure was 110.5, and their standard deviation was 12. And we're going to use this to generate a 95% confidence interval. And when they use the word approximate, they mean that. And if they use the word, oh God, it's escaped me. Do you know the 68, 95, 99.7? If they use the words empirical rule, won't that just turn into a 2? That's the only difference, right? So in this case, we know the mean, and it's going to be add and subtract 1.96. And if you want to get the standard error, since it's a relatively simple formula, I'll just write it down there, right? So it's going to be 110.5, give or take 1.96 times S divided by the square root of 100. And I shouldn't have called that S, I should have called it 12. So 1.96 times 12 divided by the square root of 100, which is 10, gets me 2.352. So it's 110.5 plus or minus 2.352. And we're going to subtract them and add them and get our interval. So 110.5, take away that guy, gives me 108.148. And it's going to be up to, well, if you add them together, I'll better do it the long way. That one, add this decimal. And we get 112.852. And they want it to 2 decimal places. So 108 point, well, let me check, I'm looking at the wrong one. It might be 3, in which case I'm good. Now, okay, let's say it's 2. So it's going from there up to 112. Well, let's say 5. Are you comfortable about that's how you find an estimate for a single mean by hand, right? Hand stroke calculator. So now we're going to do the next section. It's essentially going to be the same questions, but we're going to use SALT. In fact, the earlier questions, you could also use SALT to check. So we're going to estimate a single mean. Using SALT. Now, we are going to use SALT, but there is a bit of a complication. There are, in fact, going to be 2 versions of these questions. If your data is normal, that means it looks like that. Right, so people's height and weights is like that. If the data is normal, then when we do it, we're going to use SALT, and we're going to use the normal distribution. When the data is not normal, what does that mean? Well, couldn't your data be really heavily skewed to the left, for instance? That would not be considered, right? Symmetric, bell shapes, normal, you know, the various names we have for that. If that's the case, then you're going to use the normal distribution when you use salt. If your data is not normal, or the data is small, that's like less than, say, 10 people, right? So your sample is really small. Then you will use salt, but you will use another fella, a different distribution. And this second distribution is called the T distribution. And WebAssign is not always clear which of these two situations it is. So if you do it using this and the answer doesn't match, it probably means you should have used this guy, because you get different results depending on which distribution for the sample you use, right? So bear that in mind. If one answer doesn't work, you should use the other, right? So let's do a little bit of theory or history behind this. This has its full title is the student T distribution. And so here is a useless piece of information. This was created by a guy who worked as a quality control scientist in the Guinness factory. This is not a joke, in the Guinness factory in Dublin. And what he was doing is he was working on very small samples. And he found that when he tried to use the mathematics of the day, you know, like that question 8 we did, it wasn't matching reality, right? It said, oh, your average alcohol content is this, right? And, you know, you find out it was too strong, it wasn't strong enough, and it wasn't working. And he wanted a better way to do it. So he spent a lot of time, and he came up with this new distribution called the T distribution. And it looks very like this guy, but it's a lot flatter. And what that had the advantage of doing is that if your data was very small numbers, or if it had something weird in it, you know, like a double bump, or it was skewed, his distribution matched reality much better. And so we tend to use the student T distribution if we know that the data that you're getting is from a skewed population or a very small sample, or, you know, stuff like that. And what happened was that he couldn't use his own name when he published the paper in one of the statistic journals, right? That's what you do if you discover something clever, you publish it, right? So other people can find out about it. And so he called himself Student, right? Like John Student. And he published it under a pseudonym. And the Guinness company kind of forbid him to do it, because this was actually like proprietary knowledge, right? This gave them an edge on other companies who were doing it the old way and weren't getting very good data, and therefore were throwing away a lot of stuff because it wasn't, you know, the right alcohol level, whatever. And anyway, he didn't like that, so he just called himself Student. So the Guinness company didn't know it was him, because it was this guy Student who did it. Isn't that coincidence that that guy Student figured out, and you went, you know, these things happen, you know, people figure things out, and they got away with it. So allegedly, that is the story behind how come we know that. And if you ever go to Dublin, because I've been there, go to the Dublin distillery, right? The brewery, I should say. It's a really good, you wouldn't think it is, but it's a really good visit. They have a big spiral thing that you walk up. And as you're walking up, it shows you, you know, what it was like in the past. For instance, people in Ireland and Britain and lots of places, even children, drank beer. And it wasn't because they were alcoholics. Water would kill you. Beer has alcohol in it. Isn't one of the things that alcohol does is it kills bugs? So you actually had to drink even if it was only slightly alcoholic. So they had much weaker versions of it for kids. But it was basically like adding some alcohol into the water so it wouldn't kill you. And that's one of the things I found out. Really good. And when you get to the top, you get a free pint of Guinness as your ticket. And the guy is really good. He makes shamrocks appear on the froth. And it's a big circular glass bar, and you can look out and see all of Dublin. So it's so high up. So go to the Dublin brewery if you ever go to Dublin. It's a good visit. Okay, so how do you use it? Let me give you two examples, one of each, right? And we'll show you how salt would work. Salt does all the hard stuff. So all you really need to know is where to put the numbers into salt and where to read the answer, and you're good to go. So let's suppose that we did IQs, and we did the IQ of a nice large number of people, 200, and the average IQ of Scottish people is 105, because I'm Scottish and I'm arrogant, and it's probably not true, but we'll pretend it is. And we would like to use this sample to get the average IQ of all Scottish people, because this is only the IQ of 200, right? They could be quite different from that. And we know that IQs are normally distributed, which means I'll use this guy. So let me, I'm going to hit a salt button. I think I'm in the wrong place actually, but never mind. Let me hit the salt button anyway. Here we go. Okay, I'm ready. Let's show you what it looks like. So you go into salt, as you'd expect. Are you all looking at salt right now? Right, it's where things are hidden. Go to the one called distribution calculator. You see that one there? Sorry, inferential statistics. See that one there? Okay, and go here. Where are you hiding? Oh, excuse me a minute. I can see the T quite nicely. Where's my normal? Have you put that in a different place? Oh, okay. For the normal distribution, for some reason, it's not the same place as the T distribution. Let me check that. Yeah, go figure. There it is. Okay. Well, it is what it is. Right, so make sure it says normal. And, oh, I forgot my standard deviation was 10. Right. So the mean IQ of Scotsman was 105. The standard deviation was 10. You want a between. See that? A between. And you go here because of, what confidence interval do you want? A 90, a 95, or a 99? That has to be part of the question. What do you want? 90, 95, or 99?
No, 95.
95, okay. Now, if you want to get a 95, you do a between, and you make this guy 9, 7. You make this guy 95. There we go. And there's your start number. There's your finish. Do you see the interval? Make that 95. There's your start guy. There's your finish guy. So in this case, a 95% confidence interval would be an IQ from, say, 85.4 to 124.6. You comfortable how we got that? So let me do it. Normal distribution, click. the mean, the standard deviation. You want 95%, make that 95 and make sure that says between. And your answer is small guy, big guy. So you see your interval is from here to here. Are you okay with that? Right. Let's just say somebody said 99. Isn't that the only change? You see it? You want 90, there's the only change. Isn't it easy to do all three virtually one after the other? You don't need to change much. So we've got a 95, so let me return to the 95 one. And so I can make a prediction that based on this sample of 200 with a mean of 105 and a standard deviation of 10, that my 95% confidence interval is somewhere in this range. Right? So I could say things like, the average IQ of someone from Scotland is in that range of grade. I could also say that there's evidence that the average IQ of a Scots person is greater than 85. Would you agree? Isn't every one of those IQs bigger than 85? So couldn't I say for sure the average IQ is bigger than 85? Couldn't I also say the average IQ is less than 125? Could I say that the average IQ was 130? From this interval, would it be valid to say that the average IQ is 130? No, it's not in the interval. Could I say it might be 124? Right, might be. Yeah. If that was the case, wouldn't Scotland be full of geniuses? Because 124 is a really high IQ. On the other side, couldn't it be 86? Which means that Scotland's full of dummies, because 86 isn't, well, IQ is not actually a really good measure of intelligence anyway. Average IQ doesn't actually measure intelligence in the sense high IQ means you're clever and low IQ means that you're not so clever. IQ is actually a measure of how easy it is to learn stuff. It doesn't measure how much you've learned, because there's one big factor that IQs don't measure, and that is motivation. I have met some really intelligent people that are as dumb as two bricks because they're born lazy and they never use it to learn anything. I mean, they could if they wanted to learn, it'd be easy, but they're just not interested, right? They like rock music and that's all they do, right? So they may be really good at rock music, right? They'll tell you the name of some obscure band from 1983 that made one song that only made the top 50, and they know their names, where they lived, and everything about them. And I think, what a waste of a good brain. But, you know, that's what IQ is measuring. And then there are people who might have quite a relatively low IQ who know lots of stuff because they're actually well motivated and they spend time, right? So IQ is not a good way of talking about intelligence, but it's a measurement, so we're using it. And we're calling that process then, how you can simply just use salt. And in this case, it was the normal one that we use. And it was hidden inside distribution calculators. I am going to just put a little mute thing, getting some background feedback. There we go. There. Okay, let's show you an example of the other situation then, right? Where the t distribution was being done. So we have a small island in my story. And can't see it?
We can't see it, no.
Okay. Could you see the other stuff before I did this? Okay.
Yeah.
All right. Thank goodness that. So in my second story, there's a small island, and I managed to catch 10 ducks because the little buggers keep flying away. But I caught 10 of them, and I found out that their average weight was 3.2 pounds, and that the standard deviation was 1.5 pounds. And I am trying to find out what the average weight of ducks on this island is. And the problem I have is that the sample is small, right? And whenever you see a small sample, think t-distribution. So you might think, what is small? I think in the textbooks, it's actually anything that's kind of around about 30 or less is considered small. But you know, you might read another textbook and it's 20, and you need another one, it's 40. There's no fixed rule for it. Sometimes you just have to do a gut feeling, right? Yeah, 10's not good, right? I don't even think 30 is that good. So, you know, that works as well. And we are ready. This is all the information that we need: sample size, mean, and standard deviation, and the fact that it's going to be this new guy called the t-distribution. And I'm now moving over to salt and clicking on this guy. And I'm going to use inferential statistics. I'm not quite sure why they didn't put both of them in the same menu, but it is what it is. Right, so if I click on this one, can you see, most of these you'll never use, but they are there. Can you see a one sample t? That's what our guy's called, a one sample t. And here you put the sample mean, which for our ducks was 10. And you do the standard deviation. Why did I say 10? The sample mean isn't 10, the sample size was 10. So the sample mean was 3.2. So the average weight of the duck was 3.2. The standard deviation for them was 1.5, and the sample size was 10. And then you click confidence interval. And I guess I should have a confidence interval. So how about 95%? Does that sound reasonable? Since it's there. And then I just generate results. And the guys that you want are here. Do you see them? So somewhere between 2.13 up to 4.27. Right? So I've just rounded these guys off. And if you're interested, there's the standard error. And they've got a funny thing here called DF. It stands for degrees of freedom. And one of the things the guy, the student, I wish I knew his real name, I would call him about that. But the student t-distribution guy, what he found was that you needed to take one away from your sample size for it to work, right? So if you had 100 numbers, you had to use 99. It's a little tweak. There's kind of reasons for it, but we just, well, we don't worry about it because Salt knows to do it, right? And it's called degrees of freedom. And so I'll now return, and we have our answer. Do you notice that everything we did there was really plug and chug into the software, right? I didn't do anything myself, really. So we can say that the average weight of ducks on this island is somewhere between 2.13 pounds and 4.27 pounds, right? And I could just say a sentence like that. Could also say that there's evidence that the average weight is more than 2 pounds. Would you agree this interval, everybody is bigger than 2 pounds? And couldn't I say there's evidence that the average weight is less than 5 pounds? So if you were trying to describe this duck, you would say oh, these ducks weigh somewhere on average between 2 to 5 pounds. If you wanted to be a little bit more specific, you would say this. Of course, I haven't emphasized this yet. That was a 95% confidence interval, wasn't it? So isn't there a 5% chance that the real average is over here or over here? And when you only are choosing 10 animals, right, 10 ducks in this case, isn't there a good opportunity for a lot of variation? Maybe the reason I caught the 10 was they were the fat, slow ones. And so wouldn't this actually be an overestimate? Wouldn't the real average ducks be a little bit less than that, right? It could be, I caught all the weak, skinny ones, in which case that would be an underestimate. So you have to take that 95% into account. There could be sampling problems with how do I get the people I ended up measuring, right? Sometimes that's called selection bias, if you want a term for it, right? The bias is in who you picked. And even if you didn't mean to pick them, it's not like the ducks come out and said, weigh me, right? You know, I think they do guns, don't they? Do guns with nets and they shoot them and they catch a whole load of them that way.
I believe they do.
Yeah. So that's how it works. Are we good with this technique then, that one of these two is going to be our go-to guy, right? And if it's normal distributed and it's a reasonable size, we'll use this. But more often than not, you're going to use this one. So if you don't know which one to use, do that one, because the chances are that'll be the right one. Unless they specifically go out their way to mention it's normal, then assume it's not. That would be my advice. So I should be able to show you some questions and then maybe do some. Okay. I don't know about you, but I'm getting dizzy with changing these screens. Here we go. Oh, I don't like answers. Go away, answers. You distract the heck out of me. Okay. In each case, use the information given to compute a confidence interval and assume that all the necessary conditions are present for using the method described in 11.2 and round off your answer to 2 decimal places. Well, if I knew what section 11.2 was, I'd be able to tell you. I suspect it just means, was your sample a fair representative group, right? And there was no bias involved. It might be telling me that they're all t-distributions, which I suspect it might be as well. So that's the guys you need. So I'll have to write this down because it's going to disappear in a minute. A mean is 77, a standard deviation is 7, an n is 13, and oops, that's not good, a 95% confidence interval. Even if they didn't tell me that's a t-distribution, I can tell you right now why I'm going to use a t-distribution. One of those numbers is the clue. What is the clue?
Small sample size.
Yeah, if it's less than 30, go t-distribution, right? That's your rule of thumb. So I'll hit use salt. Okay. Unfortunately, or fortunately, isn't it already in the right place, ready to go? But can you imagine you might have done another question and it's the wrong place, right? So inferential statistics, when you want a t-distribution, one sample t. The mean in this story was 77. The standard deviation in this story was 7. The sample size was 13. Confidence interval, 95% already there. Generate the results. Our interval is that number up to that number. So I'm writing that down as what, 72.8 to 1 decimal place and 81.2. Of course, couldn't it be 3, 4, or 5 decimal places, you know, whatever one they ask you for? And that is it. Would you agree that's pretty straightforward? T-distribution, mean, standard deviation, sample size, confidence interval, whichever one of the ones you want, generate. These are your answers. That's your limit, lower limit, upper limit. We go. And oh, it's decimals, but I don't need decimals. Right. Let's return. Yeah. So the kinds of questions that you're going to use the t-distribution, number 1, which we did one of them, we did 1A. Question 2 is just basically the same thing, lots of practice. And then in question 3, they just put a story on it. Each man in a random sample of 16. Okay, already committed to a t-distribution, agreed? Between the ages of 30 is asked to do as many sit-ups as they can in a minute. Ouch. The mean number is 25.2 and that the standard deviation was 8.
I have a question.
Yes.
The mean doesn't work with the t-distribution, so I had to use normal distribution to get the answer to number 3.
It doesn't work?
It didn't work for me. It wouldn't let me put it in.
Oh, well, now that you've told me that, I'm going to have a shot at that. Now, tell you what the questions are so I know what to write down. A is the value of the standard error, right? So they want that guy. And B is going to be a 95% confidence interval, so I want that guy. And then C is just a sentence, I don't know what it says. Okay, so I'm going to hit use solve and I'm going to see if I get the same problem that you got. It's kind of amazing that you would get that. So the mean is going to be 25.2. Okay, it's taking that. Standard deviation was 8. Sample size was 16. Confidence interval, 95%. Generate results. I'm not sure what went wrong, but everything looks good, doesn't it? Do you know it was asking for the standard error, wasn't it? So that's 2. And it was asking for the interval. So it's going to be 20.9 to 29.5 to 1 decimal place. Have you tried it again, Cheyenne? And is it working now? Because sometimes weird things happen.
I'm inputting it right now.
Okay. Well, while she's doing that, let's just show you what it looks like. We already have the data. Standard error, remember it was in one of the boxes. It's 2. There's to 1 decimal place. There's my confidence interval. And we are done. Are we good? I'm not sure where my window is. Let me see what I'm sharing. Okay, I'm back to sharing this again, aren't I? Did it work okay, Cheyenne, second time?
Somewhat, but
I wish I was there. I could maybe, you know, look over your shoulder and see what's going on. It might be just your computer being weird. But it worked out pretty fine with me, so I'm kind of comfortable. Now, each one of the stories, you know, this one here, although I didn't go into the details of it, was how many sit-ups adult males could do. In the next one, it's the age of the first marriage. So
Before we move on, what?
Yeah.
It says after A, it says write a sentence that determines its value. What is the standard error of a sample mean supposed to indicate? I'm not really.
Oh, the standard error is that the average distance between the sample and the population means. So you're looking at, let's figure out which phrase they use for that one. Because sometimes they have two versions of it and they sound the same when I read them. It's the
That's a
average
sample and population.
yeah, it's the third one. The average difference between the sample and the population means over all random samples of size 9 that can be selected from this population.
Okay.
That's what
So
it's.
it's the average difference between the sample and the population.
Yeah. So
Okay.
every time you do it, there's going to be a little wiggle room, but the average wiggle room is the standard error.
Well, thanks.
Right. So next one, we're going to do a little experiment. We got time? Yes, we do. In question 4, 81 women were being asked, and this is way back in 1990, and they collected what the age they were when they, for those who got married, what the age that they get married first at, which is that. And the standard deviation is 3.6. So this is nothing to do with this question. This is just me being nosy. Does any of you know what age your mother was when she got married? And I hope it's somewhere near to 25.4 to make this seem reasonable. Does anybody know what age your mum was when she got married?
My mom was 20.
Okay.
My mom was 35. Or 30.
If you put those two together, do you know that you've already got an average of 27.5, which is an average. Some are big and some are small. Anybody, just chuck in 2 more if you can.
My mom was 18.
Okay, and 1 more.
My mom was 25.
25. Okay. So I'm going to put those guys together and we'll see what that is like today. And my experiment is scarily good. I mean, that's what, just 1 year out? So that's pretty reasonable, pretty accurate. I was wondering. You know, people, age of first marriage has changed over the last 100 years. If you went back 100 years ago, you got married a lot younger and you started your family a lot younger and you died a lot earlier as well. That's just the way the world is. Oh, I got to get this out of my head because it's in my head now. Why do Scots husbands die before their wives? Because they want to. Okay, the married ones amongst us appreciate that one. Okay, God, my brain's everywhere today. Okay, these are the only numbers that matter. We're going to do a salt of that. So here goes. I'll switch over to the guy, but I hope you're saying these questions are really the same question every time. All I'm doing is changing the numbers, which, to be honest, that is all I'm doing. So 1 sample again, check. The mean this time is going to be 25.4. The standard deviation is going to be 3.6. And the sample size is 81. And then I'm doing a confidence interval, I'm doing 95. Now that gives us a range of 24.6 up to 26.2, and that's pretty much it. Now, if you put these answers in and WebAssign says that you're wrong, then what that means is that they haven't been very clear in the question and you should have done a normal distribution, right? So I've got these numbers written down, right? 24.6, 26.9, and it didn't match. So I'm going to go distribution calculator, normal distribution, and in the normal distribution, I've got a mean of 24.5. And standard deviation is whatever it was. Am I in the right place? Yes. And I'll put in whatever it was, my 3.6. Actually, it probably should be 3.6 divided by the square root of the sample. So I should say it's that guy divided by 3, so 0.4. And I do a between, and I then make this 95, 0.95. So make sure that when you do the standard deviation, it's actually the standard error. So don't just put in 3.6, which I may have done the first time. 3.6 divided by the square of 81. So you will have to do a little calculation. I'm 99% sure that none of the questions are normal distributions, so that's probably not going to happen. But now that I've done it, the numbers that we got are 23.7 to 25.2. So let's look at what that looks like. If you do a t distribution, which is most likely, the range is that. And if you do a normal distribution, the range looks like that. Do you see that they're kind of similar, aren't they? They're in the same ballpark. They're not miles away from each other. Isn't this one just a little bit shorter than that one? Right, a little bit narrower. If you know something is normal, you know a little bit more, so it makes your estimate a little bit more accurate, right? You can shrink it a little bit. On the other hand, if you do this fella, you're assuming that the data's not great, the sample's small, whatever it might be, and that in itself extends the idea. Now, just for theory, we have two ways of tackling it, right? A t-distribution and a normal distribution. When the sample gets large, and I guess I should say very large, but what I'm talking about is about 1,000 plus. So when your sample gets to 1,000 plus, the t-distribution and the normal distribution end up being the same shape. In other words, you get the same answer. So for small sample sizes, there is a noticeable difference. For very small samples, there's a really noticeable difference, right? But when it gets big, you know, as the sample size increase, these two intervals basically merge and they look the same.
Yeah, it's not letting me do it in the normal distribution. Or did we change it to the t distribution? Or
My advice to you is to do the t distribution for every single one of these questions. My gut feeling, looking at the data, it's all small sample sizes, so I'm assuming that it is. Now, if one of them doesn't work, because there might be just one that they snuck in there, then do the normal on that one. But you'll know when you do the answers.
What's
Yep.
really funny for me is that
Yep.
I used normal distribution for 3 and 4 and got the correct answer.
So 3 and 4 are normal? Hey, thanks for
I
telling
mean,
the rest of
maybe,
us.
maybe not, but that's how I got the answer. I just used normal.
Oh,
and I
it
got the
might
correct
be the
answer.
two intervals are so close that when you round them off, you can't see any difference.
Yes.
Right, that's possible as well. Well, bear that in mind. We've been given some pre-warning that 3 and 4 may be normal, right? So you might want to do those. If you've got time, do it as a T and see if it works. In which case, it just means that both intervals are so, you know, so like each other. When you round them off, you can't tell the difference.